Okay. Any questions on what we had done? I mean, the trick is just choose a wave function, a reasonable one, such that it contains parameters. Calculate the expectation value of the Hamiltonian in terms of those parameters. Minimize it. Its minimum value gives you an idea, gives you an upper bound on the ground state energy. Now let's apply it. Now, hydrogen atom, okay, we have nice solutions. We can test it with experiments. But, I mean, we also have all the other kinds of atoms. So let's look at the helium, the ground state of helium. Now we have 2 electrons in helium, and the Hamiltonian of our system will be minus h bar squared over 2m. Laplacian with respect to the first electron, the Laplacian with respect to the second electron, plus there will be the potential energy between the electrons and the nuclei, E squared over 4 pi epsilon 0, and minus E squared over 4 pi epsilon 0, 1 over R1 plus 1 over R2. These are the positions of the first and the second electron. And there is also the interaction between the 2 electrons, plus E squared over 4 pi epsilon 0, 1 over R1 minus R2. So this is our system. There is a factor of 2 over here, because the helium nuclei have 2 electrons, 2 protons, sorry, is a charge plus 2e. So that's why we have that too. Now this is our, let's call this our H prime or VEE. This is our VEE, the electron-electron potential. And let's call the first line as our H0. So H is equal to H0 plus VEE. Now, if VEE was not there, in that case, our solution, the ground state, will be psi 100 for the first electron, psi 100 for the second electron. Now, I don't anti-symmetrize it. This is symmetric, anyway. The electrons has to be anti-symmetric, but there's also the spin, which I don't write here. So the full wave function will be this wave function times the spin wave function. The spin wave function can be anti-symmetric. So it will be in a total spin 0 state. So the total will still be anti-symmetric, although this part is symmetric. Now, in this state, H0 psi g will be the H0. We can just split it into 2 parts. H1, the Hamiltonian for the first electron, plus H2, the Hamiltonian for the second electron, psi g. Now H1 psi g plus H2 psi g. H1 psi g is an eigenstate of H1, so it's as if we have the hydrogen atom with 2 protons in the nuclei, a single electron. In this H0 there is no electron-electron interaction. H1 is nothing but the Hi is just H minus H bar squared over 2m Laplacian with respect to the coordinate of the ith electron, minus 2 E squared over 4 pi epsilon 0, 1 over Ri. And since we already assume our wave function to be each electron in the ground state, in that case, Hi psi g will be equal to now let's call that number E1. So is the energy levels, is it proportional to Z or Z squared, or now if it was the hydrogen, it would be just E1, but now we have E1 and a Z. So is the energy level proportional to Z or Z squared? Do you remember? So let's see. Energy. And remember our dimensional arguments. the energy was related with, I mean, forget about the factors plus or minus 1. It was E squared over 4 pi epsilon 0, Z times E squared over 4 pi epsilon 0, times 1 over the distance. The distance is the Bohr radius, and the Bohr radius is h bar over alpha mc. And alpha is again, now this time alpha is also proportional to E squared, but we are replacing E squared with ZE squared, so it will be Z times alpha mc. So energy is proportional to Z squared. So this we will have HI acting on the ground state, whether I is 1 or 2, it will be 4 times E1 or minus 4 E1. E1 is equal to 13.6. Oh, yes. Electron volt. So H0 acting on psi G, this is just minus 8 E1 psi G. Now let's see, what we need is H psi G, this matrix element. This is equal to, okay, psi G H0 plus VEE psi G. Part of it we already know. This is equal to minus 8 E1 plus VEE. The trouble will be calculating this VEE. Now, by the way, this this here we have psi G minus 8 E1 is equal to minus 109 electron volts. The experimental value of the ground state is minus 78976 electron volt. This is the experimental value. We are off by 30 electron volts, 50% almost. So we have to somehow get a better estimate. No. But even without parameters, we just picked up one state. And so the expectation value of the Hamiltonian should be larger than the ground state energy. So we can just, I mean, this will be, you can also see as a perturbation, by the way. So we know the ground state is non-degenerate. And we have a single state, so the correction to the ground state energy is the expectation value of the perturbation. And VEE is our perturbation. But we are not doing perturbation expansion, perturbative expansion. The first order of the perturbative expansion would also give you this number. This also tells you that the first order correction to the ground state energy overestimates the ground state energy because of the variational principle. Now let's try to calculate this VEE, which will be a bit long. Now the ground state wave function, we said that it was 100 R1 psi 100 R2. This is 8 over pi a cubed e to power minus 2 R1 plus R2 over a. Now in the next step we will introduce one parameter and see how much we will be improving it. Now then VEE would be just E squared over 4 pi epsilon 0. This is the overall coefficient. Then 8 over pi a cubed squared. We have one from psi g and psi g star. And then we have e to power minus 4 R1 plus R2 over a divided by R1 minus R2 d cubed R1 d cubed R2. So we just need to take this integral. Well, usually these kind of integrals, I mean, you cannot really take them analytically, but at least in this case it turns out to be simple. I will just do some of the steps. Now the first observation is that this one is just the square root of R1 minus R2 squared, and this is equal to R1 squared plus R2 squared minus twice R1 R2 cosine theta. Now I will just first take the R2 integral, e to power minus 4 R2 over A divided by R1 minus R2 d cubed R2. I can just assume the z direction to be the direction of R1. So then that angle theta is the theta angle of R2 in spherical coordinates. So this will be equal to 0 to infinity dr2 R2 squared from minus 1 to 1 d cosine theta from 0 to 2 pi d phi times e to power minus 4 R2 over A times R1 squared plus R2 squared minus twice R1 R2 cosine theta raised to the power minus 1/2. Now phi integral is just trivial, it just gives you us 2 pi, nothing depends on phi. The theta integral is not trivial but not complicated also. I mean, just imagine cosine theta as a single parameter itself. So the theta integral from 0 to infinity dr2 R2 squared e to power minus 4 R2 over A times R1 squared plus R2 squared minus 2 R1 R2 times cosine theta raised to the power 1/2 divided by R1 R2. And cosine theta is equal to minus 1 to cosine theta is equal to plus 1. This is my cosine theta integral. And I have a minus 1. Now, because we had our trial wave function, no parameters, and then we need to calculate the expectation value of the Hamiltonian. We need this one, the matrix element of the electron-electron interaction. So that's what we are calculating. So that matrix element is given by this integral over here. So we have to somehow evaluate it. So I mean, after the R2 integral, the rest will be kind of trivial. So let's say this will be 2 pi minus 2 pi over R1. R2 just cancels one of them. From 0 to infinity, the R2 e to the power minus 4 R2 over A. And here, if I put cosine theta is equal to plus 1, I get R1 minus R2 absolute value. Minus, if I put cosine theta is equal to plus 1, R1 plus R2. Then the task is you just divide the integral in two parts. From 0 to R1 dr2 plus R1 to infinity dr2. Your function has different behaviors in those two regions. And the rest is, well, you can evaluate the rest. There is no tricks in the rest. And the final answer turns out to be VEE is equal to plus 5 over 2 E1, which is 34 electron volts, if you put in the numbers. Now let's see, H was minus 109 electron volt plus 34 electron volt, which is minus 75 electron volt. Already we have a significant improvement. Now, well, if we were doing this as a perturbation, we wouldn't be able to argue that this would be enough, because the correction is already large. The correction is something like 30%. So we have to calculate the next term, etc. So just using perturbation theory arguments, we cannot say that this is an approximation to the ground state energy. But using the variational principle, we can say that this is an upper bound for the energy, the ground state energy. Now let's introduce some parameters. So what would you like to introduce? and something motivated by physics also. Okay, so here what we had done, we had started with a trial wave function. Here we have the nucleus of the helium. There is the electron, just you can imagine, you have the electron cloud. Our trial wave function assumed that the one electron was not really influenced by the other electron. That was our trial wave function. That was the basic physics. We assumed that there is no modification. But if you consider the cloud, there is this one electron that you are studying, let's say, there is the other cloud, but the cloud will be screening the nuclei. So if there is one cloud over here for the other electron, it will see the nuclei plus the cloud on the average charge of the cloud. So the charge that each electron will see will be mainly less than 2. So that is one possible trial wave function we can start with. So instead of taking in defining the ground state wave function, yes, that is what we will do. 1, 0, 0, R1. This was for Z is equal to 2. Psi 1, 0, 0, R1. This for Z is equal to 2. We took the ground state wave functions for Z is equal to 2. One parameter that we can choose is maybe it won't be Z is equal to 2. Now, to make it more explicit, this was our Hamiltonian, minus h bar squared over 2m, Laplacian of the first one, the Laplacian of the second one, and then we had minus e squared over 4 pi epsilon 0, 1 over r1 plus 1 over r2. Now, before we put a 2 over here. Now, this time we will put a z. But of course, in the real helium atom, that is a 2, not just z. So we have to plus z minus 2 e squared over 4 pi epsilon 0, 1 over r1 plus 1 over r2. Now, for the Hamiltonian of the helium atom, that's fixed. Well, y minus 2. No, in real life, this factor over here should be 2. That is the helium atom. So instead of 2, we put a z. If I add z minus 2 to minus z, I get 2. Minus 2. I should get minus 2. Minus 2 over there. So z's will cancel. I'm left with minus 2, which is the helium atom. The interaction between the electrons and the helium nuclei.
So you have to convert the
Hamiltonian is fixed. I mean, we cannot play with the Hamiltonian. We can play with the wave functions we choose.
yes.
So before, in this case, we had chosen our wave functions, the psi g wave function, to be an eigenstate of H0, which corresponds to z is equal to 2. Now, in this case, we are defining kind of H0 as this one.
Why don't we separate the 1 over R1 and 1 over R2?
You can, if you want. I mean, this trial wave function, you can choose whatever you want.
I got the idea that we will separate those two also from...
No, I mean, you mean just give one Z1, the other one Z2.
Yeah.
That you can also do. That gives you even a better approximation. But this will be the easiest one. Then plus e squared over 4 pi epsilon 0, 1 over R1 minus R2. Now, if you write it like this, then we will be choosing the ground state wave function as, if you remember before, it was 8 over pi a cubed e to power minus 2 R1 plus R2 over a. And remember, A for a given atom actually should be replaced by A over Z. Because if you remember A, it has this 1 over alpha. But alpha, if the nuclei has more charge, is just Z times alpha. So that's why here we have a factor of 2, because Z was just 2. Now we have a factor of Z, which is arbitrary, so this will be Z. Furthermore, here 8 is just 2 cubed. Now we will be having Z cubed. This is our ground state wave function. This is our trial wave function. This is the trial. So we have the trial wave function. We have to proceed and just calculate the now H0 acting on this one just gives me twice Z cubed Z squared E1, because each electron will have the energy Z squared minus Z squared E1. I have 2 of them. And if you calculate EE, this turns out to be 5 over 4 Z times E1. Now, of course, this is the VEE part. So the full Hamiltonian, expectation value of the Hamiltonian will be minus 2 Z squared E1 plus 5 over 4 Z times E1 plus Z minus 2 E squared over 4 pi epsilon 0 twice 1 over R. And 1 over R, in the hydrogen atom case, this is 1 over A. But since we have an atom with a nuclei which has a charge Z, this is Z over A. So what you need to do, we have the expectation value of the Hamiltonian as a function of Z. E1 is just a constant. We have to minimize with respect to Z. And it turns out that the H by dZ is equal to 0. It just gives Z is equal to 27 over 16, which is 1.69 approximately. So each electron on the average doesn't really see 2 plus 2 charge in the nucleus. It just sees 1.7 plus 1.7 charge in the nucleus, because the other electron kind of screens the charge. And if you can put in the numbers, the H min, that's the upper bound for the ground state, is equal to minus 7.5 electron volts. Well, some slight improvement. Before we had the 75. Now we have the 77 over 5, which is much closer to the ground state. Now you can, of course, increase your number of parameters. Like you can put Z1 for one of them, Z2 for the other one, for the other electron, minimize with respect to Z1 and Z2, or you can just come up with a parameter, I don't know, a wave function with hundreds of parameters. It will be a better approximation, but basically it gives the idea. Now, by the way, this method of choosing the ground state, okay, sorry, not here, in the next example. I mean, the method is kind of straightforward. Just pick up any trial wave function you like. If you have a physical motivation for your trial wave function, it's more probable that it will resemble the actual ground state, and the more it resembles the actual ground state, the better approximation you will obtain. And hence you will get a better approximation for the ground state wave function and also for the ground state energy. Any questions on this one? Let's do one more example. Let's look at the helium ion. Now, for the helium ion, no, hydrogen ion, sorry. H2 plus. So basically we have two protons, one proton, let's put it over here, this is the other proton, and then we have an electron around both of these protons. Let's say this is your R1, this is your R2, with respect to both of the electrons, both of the protons. Now we have our Hamiltonian, minus h bar squared over 2m, the Laplacian, plus e squared over 4 pi epsilon 0, minus 1 over R1 plus 1 over R2. This time we have just a single electron. So what kind of a wave function would you suggest? The simplest one. Okay, so let's assume that these protons are infinitely far away, very far away. In that case, the electron will be either in an orbit in one of them or in the orbit with the other one. So they will not be influenced with each other. Now, of course, we are bringing them together. The wave functions, the electron will be able to jump from one to the other one. But we can still more or less say that it's either orbiting one of them or orbiting the other one. So the easiest one will be the ground state with R1 plus the ground state with R2. There is a finite amplitude, it will be orbiting the first one. Finite amplitude, it will be orbiting the second one. The same, the same coefficient. Well, because the two protons are symmetrical, if you look for the ground state, it should have a symmetry. And in fact, if we just exchange the two protons, your system doesn't change. If you exchange R1 and R2, your system doesn't change. That's a symmetry. Well, if you change R1 and R2 twice, nothing changes. So if you have a symmetry, then your wave function should be an eigenstate of that symmetry. That symmetry corresponds to changing R1 and R2. We also know that this symmetry applied twice changes nothing. So if you have an eigenstate with an eigenvalue lambda, you apply it once, you get your wave function multiplied by lambda. Apply it twice, your wave function gets multiplied by lambda squared. So the eigenstates can have an eigenvalue which is either plus 1 or minus 1. Now the minus 1 doesn't give a bound state. You can just work it out, and it turns out that the energy the upper bound you obtain with the minus sign is larger than the energy of a hydrogen atom over there and the proton over there. So that doesn't tell you that there is a bound state. The plus 1 gives you a bound state. Well, if you want to study both of them at the same time, so you should better take e to the power I alpha over here. So you have this other parameter phi to minimize with respect to.
What if we had like 3 protons, 1 electron? 3 protons and 1 electron. What kind of symmetry happens then?
Well, it depends on how the protons are, where the protons are. Do they have a symmetry? For example, you have such symmetries in crystals. So again, in crystals, you have these translational symmetries, and so you can say that the wave function should have a definite property under this symmetry. Now, this is called the linear combination of atomic orbitals. Well, this is a commonly used method in condensed matter physics. So you don't even have to have the crystals. You don't have to have this ordered structure, but even if you study a large molecule and you want to write the wave function of the electron, you can just start with such a trial wave function. Of course, in that case, the coefficients don't need to have the same weight, so those are your parameters. And the parameter we have over here is actually this radial distance. This is also another parameter we have, the distance between the protons. We don't know. We just assume that when we, in this hydrogen ion in the ground state, the protons will have an equilibrium separation, the electron will be orbiting them. So we have this parameter. You can take this phi as a parameter, and this r is another parameter. And you can minimize with respect to these things. Now, the first thing, of course, you have to calculate the expectation value of the Hamiltonian in this wave function. H psi psi. This will be, let's first rewrite H as H1 minus E squared over 4 pi epsilon 0 times 1 over R2. H1 is the Hamiltonian of the first proton and the electron. The interaction due to the second proton is the additional term. This is equal to H2 minus E squared over 4 pi epsilon 0, 1 over R1. So HI is just minus H bar squared over 2m Laplacian minus E squared over 4 pi epsilon 0 times 1 over Ri. Okay. Now that will kind of simplify our expressions. H psi, this will be A squared, let's say psi 1 plus psi 2, H psi 1 plus psi 2. Again, I use psi I is equal to the ground state wave function at the point R1, Ri. This will be equal to A squared psi 1 H1 minus E squared over 4 pi epsilon 0 1 over R2 psi 1. Well, I can choose both of these representations to write H. They're equal. In this one, I prefer to keep the H1 because I already know how H1 acts on psi 1. Psi 1 is an eigenstate of H1. That is why I choose this one. Plus psi 1 H1 minus E squared over 4 pi epsilon 0 1 over R2 psi 2 plus the remaining terms. I will not write them. Well, you see, in the second line, this term doesn't contribute. Because H1 acting on psi 1 on the left is an eigenstate, so it gives an eigenvalue times psi 1, but psi 1 and psi 2, it does contribute, sorry. Psi 1 and psi 2, they are not orthogonal to each other. So that's why it contributes. This is equal to A squared. Now, from the first term, we have E1. From the second term, we have minus E1, sorry. Minus E1 minus E squared over 4 pi epsilon 0, psi 1, 1 over R2, psi 1. Minus E1 times psi 1 psi 2. This is called the overlap integral. Minus E squared over 4 pi epsilon 0 psi 1 H1 psi 2. No, not 1 over R2 psi 2. Well, the next term is just exchange 1 and 2. So we have minus E1, E2 is E1, minus E squared over 4 pi epsilon 0, psi 1, psi 2, 1 over R1, psi 1, minus E1, psi 2, psi 1, minus E squared over 4 pi epsilon 0, psi 2, 1 over R1, psi 1. Well, let's see, in fact, the last two line is identically equal to the first two line. If you write it down, I mean, it's just the symmetry that we talked about, just exchange the first and the second protons. Nothing should change. Our wave function, nothing changes actually. So the matrix elements on the second line, they're equal to the matrix elements of the first line. Basically, you just continue like this and you obtain the expression for the Hamiltonian. You just minimize it with respect to your parameter R. Now I will just write the result. I mean, I agree it's boring to just look at all these integrals one after the other one. So the H just turns out to be some E1 times some function of R over A. R is the distance between the protons. Well, there's just one additional part. There's also the proton-proton potential. So this includes the proton-proton potential. This is the potential, the total energy of our system as a whole. Now, if you plot this function f of r, f of x as a function of x, which is just the ratio of the Bohr radius to the separation between the protons, this is minus 1. So this function just has such a behavior. So this minus 1 is critical because if f was larger than minus 1, this minus 1 is the energy of the system where we have a hydrogen atom plus some other proton somewhere else. This is the energy of that system. If the energy of this configuration was always larger, f was always larger than minus 1, then that would mean the energy that if you take that's an upper bound for the ground state energy. So if the ground state energy is actually always larger than this minus E1, then to minimize the energy of the system, the other proton would just go away. So you would end up having a hydrogen atom plus a proton. The system wouldn't be bound. But the fact that this F goes below minus 1 tells you that the energy of the system when R over A has this value is lower than the energy of a hydrogen atom plus the proton at far infinity. So this tells us that the system is bound. If you started with the minus sign, the energy expression would always be larger than minus E1. It doesn't really tell you that it's not bound, but you don't have any argument in favor of a bound hydrogen molecular ion, because that's an upper bound, not a lower bound or not the exact value. Now, questions on this variational method? I mean, if you choose a bad wave function, it's quite likely that you will get a large upper bound. You don't know how below that your ground state energy is. So you cannot really prove that a given system is not bound. You cannot prove it's not bound. You can prove whether it's bound or not if you choose a proper wave function. Now, in studying molecules or in molecules, people usually do two things. One is they calculate the effective potential energies, just like we did in the previous example. The nuclear charge that an electron sees won't be necessarily the full charge of the nucleus. So what you usually do in simulating large molecules is that if you have a large atoms, the big atoms, the core electrons, the electrons closer to the nuclei, they will basically feel their own nucleus. They will not be affected that much from the other atoms in the molecule. So you just assume that they are not affected. But they kind of screen the charge of the nucleus for the other outer electrons. And so you calculate an effective potential, just like we did over here. We calculate the Z for the helium. So that is one approximation that they usually do. For this new value of the effective potential between the nuclei and the electron, you get your eigenstates for a single atom, for each one of the atoms. Okay. Then if you have this molecule, what you do is you just take linear combinations of the atomic orbitals, so-called, to obtain the wave function of individual atoms. Of course, you put some parameters which you minimize, like this one, and try to guess whether you have a bound molecule or an unstable molecule, or what are the oscillation frequencies of your molecule, etc.
Maybe for a system with many electrons, I mean, if they are like layered, then maybe coming to use this method of variation principle, and we can do optimization by first optimizing the ones for the inner electrons, and then local optimization.
Sure. I mean, condensed matter physicists, they have all these sophisticated approximate solutions. But the basic idea is this one. You pick up some physically relevant wave function with parameters, minimize the expectation value of the Hamiltonian with respect to those parameters. Other questions? Okay, so this Sunday we don't have a lecture, and so see you on Tuesday.